The fourth component of our example active treatment system is the Ponds module. Here is how the Ponds module appears when first opened in AMDTreat version 6.0. The first step is to enter the appropriate flow and water quality information. Recall that in the introductory section of this tutorial, the water quality and quantity information for our example site is listed. The pond module requires that both a design flow and a typical flow be entered. The design flow will be the basis for which the pond's hydraulic capacity is determined. Typical flow, as discussed in the previous lime slurry module, module 2 of our example, should approximate the average flow the system will be treating on an annual basis. For the pond module, typical flow rates and metals concentrations are used to estimate sludge production. In our example case, we will assume that the typical flow is what we have estimated to be our continuous mine pool pumping rate of 300 gallons a minute. In other treatment scenarios, especially sites having gravity discharges, typical flow will usually be less than the design. In passive treatment situations, ponds often serve two primary functions, the first of which involves a chemical process providing sufficient time for metals oxidation to occur. The second process is a physical one, which allows for sufficient retention time and storage volume for those oxidized metals to precipitate from the water column and be stored until sludge cleanout is performed. Typically, in the case of an active treatment system, and as in the case of our example, the pond's primary function will be the physical aspect of allowing enough retention time for adequate precipitation of already oxidized metals along with sludge storage. The chemical process, metals oxidation, has already been completed through lime addition. pH adjustment allows for very rapid, almost instantaneous metals oxidation. The result being that oxidation has occurred before the water exits the reaction tank. The water quality and flow input section for our example site. Note that because of that chemical addition, we will assume that all of the iron present has been oxidized and is now in the ferric Fe+3 form. The next section of the module is pond design and focuses on sizing the pond component. The first sizing option labeled is oxidation/settling/sludge. This option allows us to enter the depth for each layer of the pond, including freeboard, oxidation, settling retention, and sludge capacity to size the pond. This is the method we will use for our example system. The freeboard layer is the top layer of the pond between the top of the water layer and the top of the embankment, and typically contains an emergency spillway feature that is necessary to prevent breaching of the embankment resulting from flows in excess of the design flow or with a problem related to the water level control structure. We would typically select to specify the freeboard top length and width dimension in feet where the pond is an existing feature and where we would want to know the dimensions or where the land area available at the site is limited and the size of the pond must be constrained accordingly. Please note that if we decide to manually enter the freeboard top length and width dimensions as the sizing option, the depths of each layer are still able to be manipulated, but the bottom length to width ratio in the next section is not. The next section, called System Properties, is where adjustments can be made to the pond inside slope, the bottom length to width ratio of the settling retention layer, and the excavation unit cost. For our example, we will keep the default values for these three items. The next section is pond layers. For the first item, freeboard layer, we will accept the default value of 2 feet. The next layer, oxidation layer, is the pond layer where metals are oxidized. For our example, we will minimize the oxidation layer, selecting a depth of 0.10 feet rather than accept the default value. As previously discussed, our goal is to optimize the settling and retention sludge storage attributes of the pond. As such, the sludge settling and capacity depths will be increased to 4 and 6 feet respectively. For the settling retention layer, the user can specify both the depth and the retention time within this layer, which relates to the sizing of the pond. The optional sludge capacity layer is the bottom of the pond where the settled solids accumulate, forming sludge that must be periodically removed using one of the sludge handling and disposal methods to be discussed later in the annual cost input section. The final layer is where the user selects if a liner is desired, and if so, what type of liner material will be used, clay, synthetic, or geosynthetic clay. Here we will select the option for including a synthetic liner. The hydraulic structures section is where we can specify piping, use of baffles, and any other appurtenances or other items needed for the pond component. For the piping, we can select to use either the AMDTreat piping calculator or a user-specified piping layout by checking the appropriate box. The AMDTreat piping calculator was selected for our example, and all the default values are used, with the exception of the length of the influent-effluent piping, which has been changed from 100 feet to 50 feet. The alternative option, entitled User Specified Piping Layout, simply requires us to enter the custom pipe name, the length of the pipe, and a unit cost for the purchase and installation of the pipe for 3 possible different types of pipes to be used in the pond. The next item is to select whether a baffle or curtain is required and whether to allow AMDTreat to estimate the length of the baffle needed, or if the user will specify the baffle. An AMDTreat estimated baffle assumes one baffle, which is most commonly a floating vinyl curtain, and will be used across the entire width of the pond at the approximate midpoint that is perpendicular to the incoming flow path. For our example site, we will choose 2 baffles with user-selected lengths that corresponds to the calculated top pond width. The appurtenances Other Items section allows the user to include purchasing a pump for sludge handling, valves, an intake structure, flow distribution structure, water level control structure, outlet protection structure for the pond by specifying the quantity and the unit cost for each item. Please note that each item under Appurtenances Other Items has a default quantity of 1, so if any item is not needed, the quantity must be changed to 0 or the unit cost set at $0. For our example, we will choose to accept default value. The Other Capital Items section allows the user to specify any items that are needed as part of the pond construction that are not captured within the module, and allows us to enter up to 5 different items, including a description, quantity, and unit cost. No other capital items will be selected for our example site. The annual cost input section is where we can specify items that affect sludge generation, sludge handling, and sludge disposal related to the ponds feature. The first section, sludge generation, allows us to manipulate parameters that affect the quantity and composition of the sludge generated, as well as the expected percent solids of the raw sludge within the pond and the dewatered sludge following handling, process, and preparation for disposal. Both calcite and miscellaneous solids can be estimated as contributors to the generation of sludge within the pond. For our example site, using lime treatment, we will assume percent solids of the settled sludge will be 10%, and that 5 milligrams per liter of calcite, as calcium carbonate, will precipitate along with the AMD metals as a result of using a lime treatment pH adjustment process. In other words, the treated water will be supersaturated in terms of calcite, and some calcite precipitation is to be expected. In the sludge handling section of the annual cost input, we can define the method of sludge removal from the pond, or select a generic unit cost for sludge handling and disposal as a composite of all the removal and disposal methods if the method of sludge handling is not yet known. For our example, we will choose sludge removal by pump method and assume that the sludge is pumped from the pond to an on-site drying bed. For our example, we are choosing an electric pump and changing the default electrical cost to 8 cents per kilowatt hour to be consistent with the costs that we have estimated in the preceding treatment modules. The last item under the annual cost input is sludge disposal. After defining the method for removing the sludge from the pond, to capture all of the annual costs for a pond, it is important to capture the cost to dispose of the sludge after it is removed and dewatered. By default, Enable Sludge Disposal is selected, so if we do not wish to consider it as part of the annual cost, then this box should be on select. If the dewatered sludge is to be taken to a landfill for disposal, there is a landfill tipping fee enabled to input the unit cost. For our example, we will assume that the dewatered sludge is removed from the on-site drying bed on an annual basis and disposed of at a landfill. Shown here are the assumed dewatered percent sludge, landfill fees, and trucking costs for our example site. We have now completed all of the input necessary to generate the summary numbers shown on the right side of the module. The pond sizing summary on the top right side of the module provides a wealth of information about the features based on the user input from the right side of the module. From the various layered dimensions to the surface area, total pond depth, volume, and retention time of each layer, the length of the baffles needed, the volume of thickened and dewatered sludge, and the frequency of sludge removal based on the sludge capacity, layer volume, and thickened sludge volume. The total retention time of the pond is 49.41 hours. The estimated freeboard top length and width values are 176 feet and 106 feet, respectively. The capital cost section summarizes each of the primary components for the pond feature and provides a total cost to construct the pond based on the user-specified features and sizing criteria. The capital cost of the pond is estimated to be $74,877. The annual cost section includes the costs associated with operation and maintenance, sludge handling, and sludge disposal for the pond. For each of these three items, the user can accept the default estimated values from the module or input known values for any of them where appropriate. For the operation and maintenance, we will change the percentage of capital cost value to 3.5%, which results in a total annual cost for the pond to be $27,001. Finally, the net present value for the pond feature is shown to be $567,779, and it represents the cost to operate and maintain the pond structure for an anticipated lifespan of 75 years. Now, if we revisit the main user interface after setting up the four components of our example active treatment system, we can see the capital cost, annual cost, and net present value shown in the tile for each component. Also, at the bottom of the main user interface, there is a summary for the entire system showing the capital cost, the annual cost, and the net present value. The project footprint in acres is also provided for all of the system components combined, and our system area is estimated to be approximately 0.65 acres. That concludes the tutorial for setting up an example active treatment system in the AMDTreat software version 6.0. For more detailed information about the modules, please see the respective help files provided at the AMDTreat website.